Dear students, we have discussed about the DC characteristics of operational amplifier. Now we are going to discuss about the another important question in this first unit, that is nothing but the AC characteristics of the operational amplifier. So in the DC characteristics we have discussed about the bias current, offset voltage and thermal drift, and it is mainly deals with the DC response of the op amp. And for the small sinusoidal signals, AC characteristics such as frequency response and slew rate has to be discussed. We can discuss about the frequency response. So frequency response is nothing but it is gain versus frequency or frequency versus gain. So how far the frequency increases, what happens to the gain? So whether the gain decreases or increases, we are going to see about that. So normally good frequency response is such that whenever the frequency is increased, the gain of the particular amplifier must also get increased and it should not get decreased. So for an ideal operational amplifier, we have an infinite bandwidth. So when we express that particular bandwidth in the decibel, and it will be around some 90 dB, okay, for audio frequencies also. So but when we go for the practical op amp, what happens is the gain mainly decreases at the higher frequencies. So normally the gain should remain constant at the higher frequencies, but what happens here is the gain decreases at the higher frequencies. This is mainly because of the capacitor component which is present at the op amp. You can see the capacitor component. This is the capacitor component. Because of this capacitor component, what happens? The gain decreases. So this capacitive component, it has been present because of the physical characteristics of the device, okay, and the internal construction of the op amp. Normally capacitor will be added to the circuit for cascading the circuit and also to avoid some of the noises. So for that purpose only we will be adding some capacitance, and because of the capacitance, what happens is the gain of that particular circuit will get reduced. So here you can see a capacitance. This capacitance, what happens, it produces a corner frequency or a break frequency. So for an op amp, a corner or a break frequency where all the capacitor effects can be represented by a single capacitor. So this particular single capacitor will be called as a pole, and because of this pole, that is the combination of R0 and C will be considered as a pole, and because of this pole, what happens, there will be a 20 dB decade of gain. Okay, there will be a 20 dB decade of gain. So we can see the general circuit of the op amp. Where you will be seeing the two end V1 and V2, and VD will be the difference between V1 and V2, and RI will be the input impedance, and AOL will be the open loop gain. This open loop gain must be infinite, and when we express it in decibel, this open loop gain will be in the 90 dB. And because of this capacitance, what happens, this R0 and C will be constitute a pole, and because of this pole, what happens, there will be a slight 20 dB decay. So normally the output voltage V0 is represented as follows. V0 is equal to minus JXC divided by R0 minus JXC into AOL VD, where XC will be the susceptance and R0 will be the output impedance and AOL will be the open loop voltage gain. And the gain of op amp is being denoted as A, and the gain of op amp is calculated as V0 by VD. Okay, normally the gain of op amp will be calculated as V0 by VD. So when we substitute VD here, that is VD is being gone here, so V0 by VD is equal to A. What we will be getting? We will be getting AOL divided by R0 minus JXC divided by minus JXC. So this particular equation can be rewritten as AOL divided by 1 plus JXC into R0. Okay, so this particular equation can be rewritten as AOL divided by 1 plus jxc into r naught, where j represents the complex conjugate. Okay, so it is nothing but the imaginary part. So after rewriting this equation, we will be getting the equation as AOL divided by R naught divided by minus JXE. So when the complex value J comes over to the denominator, it will be substituted in the negative part. So we will be getting A is equal to AOL divided by R naught minus JXE plus 1. And when we rewrite this particular phenomenon, we will be getting A is equal to AOL divided by 1 plus J 2 pi f r naught c. Okay, so when we rewrite this phenomenon, we'll be getting this particular answer. And when we substitute f1 is equal to 1 by 2 pi rc. Okay, when we substitute f1 is equal to 1 by 2 pi rc, we'll be getting A is equal to AOL divided by 1 plus j f by f1. This equation, you must remember, it is a very very important equation. Based on this equation only, we are going to find out the decade. Okay, so this particular equation AOL divided by 1 plus j 2 pi f r naught c can be rewritten as A is equal to AOL divided by 1 plus j f by f1, where f1 is equal to 1 by 2 pi r naught c. So this f1 is called as the corner frequency, and this corner frequency will be denoted at the 3 decibel level of the gain. Okay, this f1 is called as the corner frequency, and the corner frequency denoted at the 3 decibel level at the gain. Now we are going to discuss about the compensation techniques for the AC characteristics. The main compensation technique we are going to use here is the external compensation technique and the internal compensation technique. And especially in the external compensation technique, we are going to discuss about the frequency compensation, because the frequency increases, which mainly decreases the gain. So that is the problem, is it so? So you can see here the frequency is increased and the gain is being decreased here. So in this cases, we need to go for some compensation technique to avoid the decrease of gain and to avoid the noises. So we are going for the frequency compensation technique. When large bandwidth and lower closed loop gain are required, suitable compensation technique are need to be employed. So one of that suitable compensation technique was the external frequency compensation technique. This external frequency compensation technique can be applied for the low closed loop gain. Okay, so it cannot be applied for the larger gain, it can be applied for the low closed loop gain. So what it does, it is divided into mainly two types. One, it is called as dominant pole compensation, and another one is called as pole zero compensation or lag compensation. It mainly alters the open loop gain so that the rate of minus 20 dB per decade will be slightly decreased when compared to the original one. We can go for the dominant pole compensation. The pole here, it has been mentioned is nothing but the RNC. I have already informed you that pole is nothing but the RNC. So this RNC is calculated as pole, and this R and C together added at the output end of the amplifier. So here we have to assume A as the uncompensated transfer function or uncompensated gain of the op amp in the open loop condition. That is, A is the gain measured before compensation technique, and this dominant pole is generally introduced in this op amp by adding an RC network in series with the op amp. Okay, that is, we are adding an RC network, that is the resistant capacitance network, in series with the op amp, so that a dominant pole has been created and the compensation is applied to the particular circuit. So now the compensated transfer function or compensated gain will be calculated as A dash, and it is denoted as A dash is equal to V naught by Vi. Okay, A dash is equal to V naught by Vi. So in another form we can represent it as A dash into minus j by omega c r minus j by omega c, where V naught by Vi is nothing but the A, and this minus j by omega c r minus j by omega c is mainly occurred because of the addition of this RC network. This first one is the because of this capacitance, and this r minus j by omega c is the combination of R and C. When we further solve everything, at final answer we will be getting A is equal to A dash is equal to A divided by 1 plus j omega RC. Okay, after solving it by proper substitution method, the final answer we get was A dash is equal to A divided by 1 plus j omega c RC, where omega is represented by the 2 pi RC, and that 2 pi RC can be represented by beneath, and we will be getting A divided by 1 plus j f by 1 by 2 pi RC. So this is the general formula for the open loop frequency compensation technique, and at final we are getting the answer as A dash is equal to A divided by 1 plus j f by fd. So here this particular 1 by 2 pi RC is considered as fd, and we are dividing this whole thing divided by 1 by 2 pi RC, and we are getting A divided by 1 plus j into f by 1 by 2 pi RC. So we are dividing it, so we are getting A into 1 plus j f divided by 1 by 2 pi RC. So that is represented as A dash is equal to A divided by 1 plus j into f by fd, where fd is considered as 1 by 2 pi RC. So here this fd is considered to be the corner frequency, and when we imply this particular amplifier with 3 more network, that is, if we are using only one RC network, and if we use some RC etc., 3 networks, and we will be getting the final equation such as like this, that is A dash is equal to AOL divided by 1 plus j f by f1 into 1 plus j f by f2 into 1 plus j f by f3. So the first equation what we found was A dash is equal to A divided by 1 plus j f by fd or f1. Fd can also be written as f1. This has happened because we have substituted only one RC component. If we substituted 3 RC component in this circuit, the equation what we will be getting will be this particular equation. This is the final equation. So if it happens, means we can able to see the frequency response of the particular circuit here. So you can see here frequency response, that is the open loop gain versus the frequency curve. So this is the frequency, and open loop gain has been given here. So for f1 there is a 20 dB f1 there will be a 3 dB decay, after f1 there will be a 20 dB decay, and after f2 there will be a 40 dB decay, and after f3 there will be a 60 dB decay. So the disadvantage of this frequency compensation technique is it is suitable only for the closed loop gain, and especially for the lower gains. It cannot be applied for the higher gain. So for the open loop gain, it majorly reduces the bandwidth, but its main advantage is it improves the noise immunity. So noise immunity, if it get improvement, what happen? It reduces the major amount of noise, so that the signal amplification will be very easy, and the output what we obtain will be perfect. So that is the major advantage of this particular dominant pole compensation. The main disadvantage is reduces the open loop bandwidth, but the major advantage of this dominant pole compensation is the improvement of the noise immunity, so that the noise frequency component will not be available in this amplifier. So we are adding an RNC. This RNC combination is called as dominant pole, and this dominant pole play a major role in reducing the noise immunity in the amplifier. So you can see here, and when we take the modulus to the above equation, so modulus means removing the imaginary part, we will be getting AOL divided by root of 1 plus f by f1 square. Okay, modulus is denoted as a modulus is equal to AOL divided by root of 1 plus f by f1 square, and phi is equal to tan inverse of f by f1. So these two equation, modulus A and phi, are called as two parts, and one will be the magnitude part and another one will be the phase part. Okay, so one will be the magnitude part and another one will be the phase part. So we can discuss about the magnitude response of the frequency and the phase response of the frequency one by one. The first graph mainly indicates the magnitude response of the frequency. So magnitude response of the frequency, we can able to find out from the above equation, that is mod A is equal to AOL divided by root of 1 plus f by f1 the whole square. So you can able to find out, or you can able to infer from this particular diagram. So the gain of the particular op amp remain constant, and there is a particular frequency where it decays 3 dB, and after that particular frequency you can able to find a 20 dB decay. So what we can infer from this is, for a frequency f less than f1, the magnitude of gain is 20 log AOL in dB. That is, for all the frequency here, that is which is less than f1, the magnitude of gain will be constant, and it is nothing but the 20 log AOL. Okay, and at the particular frequency f1, when f is equal to f1, there will be a slight decay of gain, and that is calculated as 3 dB. So at frequency f is equal to f1, gain is 3 dB down from the normal value of the AOL, and the phase angle at this particular point will be 45 degree. And for the f greater than f1, the gain rolls off 20 dB per decade. So that means for each and every 10 frequency, the gain will be reduced to 20 dB per decade, or 6 dB per octave. Okay, so what we infer is, when the frequency is less than f1, the gain value remain constant. At frequency f1, the gain value decreases 3 dB, and at the frequency greater than f1, the gain value decreases 20 dB. That is the most important one. And the next one is nothing but the phase one. Okay, phase component. And in this phase component also you can able to infer, when the value of frequency is less than f1, the phase angle will be 0. You can see here, this is the phase component. So when the value of frequency f is less than f1, that is for all the frequencies which are available in this part, the phase angle will be 0. And frequency f is equal to f1, a phase angle will be minus 45 degree. That is, the phase angle will be lags behind 45 degree to the normal one. And when the frequency increases, the phase angle lags at minus 90 degree. So this is what we infer from the phase component. So there are two components I said. One is the magnitude component, that is mod A, and another one will be the phase component, that is phi, and it is calculated as tan inverse of f by f1. So for both magnitude as well as the phase component, when the frequency is less than f1, the gain will be remain constant, and there will not be any decay in gain, and there will not be any phase difference. But when the frequency is f1, that is f1 is nothing but the corner frequency, there will be a 3 dB decay in the 3 dB decay in the gain, as well as the phase will be lagging at the 45 degree. And similarly, when the frequency f1 is when the frequency f is greater than f1, in the gain you can see a 20 dB decay, that is in the magnitude, and in the phase you can able to find the 90 degree decay. So these are the two inferences we have been found out from the frequency response, and next we are going to check how we are going to overcome these scenarios. The next compensation technique what we are going to discuss is pole zero compensation. We have already seen that the dominant pole compensation is mainly suitable for the only low frequency amplifiers, and for the improvement of bandwidth and high frequency amplifiers we have to go for the pole zero compensation. This pole zero network introduces a new pole at sufficiently low frequency and zero at the higher frequency. Okay, so you can see this is called as a pole and this will be called as a zero. Okay, so an addition of resistance and capacitance in series will be called as a pole, and a separate resistance add will be called as a zero here. And this R1 is considered as Z1 impedance, and this R2 C2 will be considered as impedance Z2. So here we are calculating the uncompensated transfer function as A, and it has been changed by adding pole and 0. Pole is nothing but the addition of resistance and capacitance, and 0 is nothing but the resistance. So the pole will be added at the lower frequency n, and the 0 will be added at the higher frequency n. So when we go for the derivation, so the derivation you can just have a go through. In the exam point of view, you don't want to write all the derivation, so it is enough to draw the diagram, and you have to write the value for A and you have to write the value for A dash, because this AC characteristics you have to write both the frequency response as well as you have to write the dominant pole 0, and you need to write the slew rate also. So it's not possible to write each and every line derivation, so you have to you can go through the derivation and you can directly come and write the answer for this particular question. So the pole 0 compensation, they have been calculated. The value for A is equal to A dash is equal to 1 plus J F divided by 1 by 2 pi R2 C2, 1 plus J F divided by 1 by 2 pi R2 plus R1 into C2. So the value will be denoted as this one. That is, this is the particular equation which you need to remember. This equation which I am just marking, you can see here, you can just see the arrow mark here. This is the equation you need to remember. As I said, you don't want to derive each and every derivation, because you will not be having enough time to write the other question. So you have to write what is meant by pole 0 compensation and where it will be applied. So what is meant by pole and what is meant by 0, you have to write it, and you have to write about the what is the uncompensated function. Then after you can directly come to this particular equation and you can write the answer this particular equation: 1 plus J F by 1 by 2 pi R2 C2, 1 plus J F divided by 1 by 2 pi R2 plus R1 into C2. So the F1 will be calculated as 1 by 2 pi R2 in C2, and F0 is considered as 1 by 2 pi R1 plus R2 into C2. So when you substitute this F1 and F0 in the above equation, you may get the value of A or A dash will be 1 plus J F by F1 divided by 1 plus J F by F0. So this compensating network is mainly designed to produce 0 at the first corner frequency and pole at the another corner frequency. So this 0 will be looking after the lower frequency function and the pole will be looking after the higher frequency function. So you can see here the 0 will be adding the compensation at the first corner frequency F1 of the uncompensated transfer function. The 0 will cancel the effect of pole at F1. So the pole effect at the F1 will be compensated or cancelled by 0. The pole of the compensated network will be deleted at the lower frequency, and this particular pole will be having a major part only at the higher frequencies. So the pole effect will be largely seen in the higher frequency and the 0 effect will be largely seen in the lower frequencies. So what happens is, for the lower frequencies the compensation will be obtained, and again for the higher frequencies the compensation will be obtained. So this pole 0 compensation is mainly suitable for lower as well as the higher frequencies, whereas the dominant pole compensation is only suitable for the lower frequencies. And next is nothing but the internally compensated technique or internally compensated frequency technique, and this technique will be done for broad bandwidth of the uncompensated op-amp. And we have know that, for example, we can consider an instrumentation circuit. The op-amp is normally required to amplify relatively by slow changing the signal, so it does not require high frequency response. So in this particular thing we can use the internal compensated op-amp. This op-amp IC741 mainly contains a capacitance of 30 picofarad. It mainly shuts off the signal current and reduces the available output signal at the higher frequencies. So this compensation technique mainly take place internally and it produces a stable circuit. So this stable circuit is obtained internally by using the compensation of capacitor, which is designed internally while constructing the op-amp. So this internal compensation technique is applicable especially when we does not require any high frequency response and it is suitable for the slow changing signals.